Okay, so thanks very much for coming along, everybody. It's nice to be here. One thing, Rick, isn't it? Rick failed to mention is my phone is here because my wife is 39 and a half weeks pregnant. Right? So if that rings, there may be a sudden, you may see me heading for the exit. If that happens, my glamorous assistant, well, actually, my glamorous assistant wasn't available, but Neil, who's up there, will rush to the front and take over live. So, oh, right. Damn! Always insult the boss at the start of a talk to win over the audience, if not the boss. So, what on earth's this about? Murphy versus Satan, and okay. So, what I'm going to talk about is what we mean by this idea of Murphy versus Satan. So, it's like Murphy's law versus something else. And I'll tell you what that is and what we mean by it. Unfortunately, it's quite a lot of bad news. How many times do you open the newspaper recently and, oh, another device has been hacked, or another car has been hacked, or something that really matters has been hacked? Recently, this morning on BBC News, it appears a hospital, it was up north somewhere, a hospital has been basically rendered inoperable by some sort of malicious activity on their computer system. So this, bad stuff's happening, folks. And there's quite a lot of worrying stuff going on. If you talk to the people from the new National Cybersecurity Centre, it's pretty scary. So what, as programmers, can we do about it, is what I'm interested in. So that's the good news bit. There is some good news, I'm pleased to say. We do know some stuff about how to do it. And then I'll leave you with a final thought. And then I will set you some homework. Ha! You didn't think you were going to get homework, did you? But you are. Because if I leave you with nothing and you go away from today and go, oh yeah, that bloke said something I can't remember, I will have failed. So I want to inspire you to actually go and do something as a result of coming along today, rather than just going back to your day job and going, oh, whatever. Okay, so what do we mean by Murphy versus Satan? So, we at Altran, we've often, for about 20 or 25 years, been involved with building safety critical systems. So we work with the likes of Rolls-Royce, building jet engine, the digital engine control systems in the really big Rolls-Royce jet engines. We build tools used by the National Air Traffic Services people, the tools that defends your well-being when you fly on an aeroplane and you're out of the UK. Okay, we built that stuff. And would it surprise you to learn that it never fails? The tooling we built for NATS has been online, operational, for over 5 years. And it's basically never been unavailable in that 5-year period since we deployed it. So how do we do it? How do we build stuff like that just doesn't fail, even sometimes under malicious attack? So we talk about Murphy's computer, meaning Murphy's law, so a computer that just fails, but possibly fails randomly. It can wear out now and again. Maybe a fuse blows, the power supply fails, something like that. Well, okay, Murphy's computer fails randomly. With a little bit of energy and thinking, you can get them to fail silently. Failing silent is generally good because you just want a computer to fail and shut up so that it doesn't, flood the network with junk and behave maliciously. So fail silence is a fairly easy thing to engineer. And that's reasonable. So we get stuff like this. This is probably a bad thing to have on my slide today, infant mortality. Who put that on there? Dear, oh dear, don't show that to my wife. Early in their lifespan, some computers just fail straight away when you switch them on because the electronics has not been soldered together properly and stuff. So you get this infant mortality. There's constant random failure. And then we get things that wear out late in life after about 20 years or so. Stuff sometimes just tends to wear out and die. So we get this observed failure rate that does that. That's called a bathtub curve. For those of you into reliability engineering, that's very common. It's very well understood statistically, and we can build systems to deal with that by, how many of you have flown on a commercial aircraft and paid money to fly on an aeroplane, right? How many of you flew on a commercial aeroplane, paid money to be on the airplane, and the airplane only had one engine? Did you jump out of it?
They took it back to the...
Okay, it's very rare to get on an aeroplane that's only got one engine, unless you intend to jump out of it, or maybe, some general aviation. But commercial aviation, you'll find planes have 2 engines or more. There's a good reason for that, because it's always a really good idea to have a spare one. So we employ things like redundancy to build safety critical systems. We have a spare. We have 2 power supplies, 2 computers, 2 networks, 4 networks, 4 hydraulic systems, 2 wings. That's a good idea. on a plane, you know, there's usually a spare one. So to build ultra-reliable systems, we kind of know how to do that. But once in a while, you get this effect. But yeah, oh, so what? That's okay, because we've got a spare one knocking around. So Murphy's computer we can cope with. There are some examples of staggeringly reliable bits of computer stuff out there that have been working for 30 or 40 years. Some of the railway signalling infrastructure in this country is stuff that's been out there sitting in the rain for 30 years, and it hasn't failed. It's astonishing. Satan's computer, oh dear. So this is the flip side. Satan's computer is very different. Satan's computer fails maliciously. It fails in the worst possible way, at the worst possible time, and possibly even sort of intelligently and maliciously. Possibly because somebody else is forcing the computer to misbehave in some intelligent way. So this is an entirely different proposition. This is the problem of building ultra-secure systems, especially if these systems are in some sort of open environment where other people can get at them and poke them. It's reasonably easy to build stuff like this if you've got an air gap and a bank vault and a Faraday cage available. You can lock them away behind the network, you know, unplug all the network cables. Okay, fine. But stuff that's actually open, pretty difficult to deal with this environment. The phrase programming Satan's computer actually comes from this chap. This is Professor Ross Anderson, who's Professor of Security at Cambridge. He's written a fantastic book about security engineering. So Ross and Roger Needham in 2005 coined this phrase, programming Satan's computer, to give you the impression that it really is that hard to get computers to behave themselves and when we're in this malicious environment. So some examples. You open the newspapers. Every single week you see things like this. Jeep recalls God knows how many vehicles. The Jeep hack was astounding. I mean, this was an entire vehicle that was basically taken over by two guys with a laptop and a mobile phone from 10 miles away. They were able to take control of the steering and the brakes and the whole deal. I think it's in Wired, the magazine, the report of how they did it. It's an astonishing piece of hacking. It's also an astonishing piece of incompetent engineering from Jeep. And it's incompetent. It's not a glitch. Please, all of you, please stop using the word glitch. It sounds all kind of cute and fluffy, the word glitch. It's not a glitch. It's incompetence, okay? To allow that to happen. Why are you laughing, Steph? It's not funny, okay? Toyota, another example. If you look at the court proceedings of Toyota's litigation in Oklahoma, the defendant was somebody called Mrs. Bookout, B-O-O-K-O-U-T. So if you look up Bookout versus Toyota, look at the court proceedings of what happened to Toyota in court. They got themselves in a terrible muddle with their engine control, throttle control software, and this was an example of this unintended acceleration in Toyota cars, which actually did kill people. And people died as a result of this. Toyota were facing millions or billions of dollars of fines. There is a long queue of litigation waiting against Toyota in the States. And they got themselves in a terrible muddle. I do recommend reading the expert witness testimony in this case. It's publicly available, and it's amazing, you know, the kind of trouble they were in and the mess they'd made. More recently, Mitsubishi Outlander, hackable because it's a Wi-Fi access point. The car is an access point, and some people discovered by reverse engineering the protocol, you could log into the car with an iPad and bang open all the doors, turn on the aircon, turn on the windscreen wipers, all sorts of stuff. This is done by Pentest Partners. Really exciting. Most recently, okay, you know, botnets, denial of service attack 2 weeks ago using things like webcams. Pretty embarrassing. So it's kind of embarrassing, really. Why can't we do better? Why is this so hard to get right? An important question is, will you be next? Is your company going to be on the headline of the Financial Times tomorrow morning saying, oh, big system got hacked, oh dear? And what's that going to do to your share price, your reputation? If you're a startup, it might just put you out of business completely. You know, you may just disappear as a result of one of these things. It's worrying. So the bad news, why is it so damn hard? So here's a list of things you might want to be worrying about in this world. So firstly, the game is rigged badly against you. The bad people are much smarter than you. And I don't care how smart you think you are, they're bigger than you. They're smarter than you. They've got more money than you, more time and motivation. So they talk about these things called persistent, what are they called? persistent threats or something, and they talk about state-level actors. Basically, you're up against the government or a government agency who are pretty good at this stuff. The organised crime people are very good at this stuff now because they have access to the technology very readily. They didn't really develop it, but it's just out there. You can get it. So, yeah, it's like, trying to do judo when you're 40 kilos lighter than the other dude. It's no fun at all. In this case, sumo, not judo. But anyway, you get the idea. Asymmetry of efforts. This is really tricky. As a developer of software, the rational thing for me to do is to try to remove all the so-called vulnerabilities or defects or bugs in my code. Because if I leave one, somebody's going to find it. You can make it harder for people to find such defects, maybe to a point where they'll just sod off and go and attack someone else, which is a reasonable strategy at a grand scale. But basically, I want to get rid of everything, all the bugs, to be sure. An attacker needs to find just one of them. So there's a real big asymmetry there in how much effort might be required. Getting rid of all the bugs in your code is pretty hard, right? Because that's just the way it is. Asymmetry of knowledge. This is a really bad situation, basically. As a developer, maybe you're writing code, you need to get rid of all the defects and the vulnerabilities, whatever you want to call them. Well, there's the defects and vulnerabilities that you know about. So the ones that we all know about, like, you shouldn't have buffer overflows in your code. You shouldn't have arithmetic overflows. You probably shouldn't divide by 0. You shouldn't allow unvalidated data to get through your system and then end up being used to form a database query or whatever. All these usual things that we all know about. You can read them online, the top 10 blah blah attacks of all this stuff. So there's all the ones that we already know about. But there are attacks that other people know about but you don't, which is a bit worrying, because how do you defend against those? The so-called 0 days and all that sort of stuff. There's a big library of them out there that you don't know about yet. So how are you going to cope with that? And then there's a really worrying set. There's a whole bunch of attacks and vulnerabilities that nobody knows about yet, because they haven't been discovered yet. These are I nearly said the wrong word. Rumsfeld. I nearly said Trump. That was, dear oh dear, don't bring him up. Rumsfeld famously talked about the unknown unknowns, and all this sort of stuff is very difficult to cope with. So the unknown unknowns are the vulnerabilities that you don't know about. So an example of that, we were working on smart cards in about 1997. We built the root certificate authority for a smart card system. And in about 97, the smart card manufacturers, people like Philips and Hitachi, that were making the ICL microprocessors that go in your pocket, like on your Oyster card or your bank card. This was quite early days for that industry. In about 97, they were in great shape. They thought everything's cool. They're going to roll out all these smart cards and produce millions of them. Everybody's going to have one. Unfortunately, this guy came along, Paul Cocker, and he said, hang on a second, if I plug in a digital oscilloscope and an ammeter to your smart card and do lots of testing of the smart card and measure the power consumption of that thing, I can extract the cryptographic material from that smart card, the supposedly secret crypto stuff. So Paul Cocker came up with this thing called differential power analysis. And the entire smart card industry went, oh, crap, we're broken, we're dead. And they had to go back to the drawing board and redesign the silicon to make the silicon resistant to this DPA attack. And before this was published, nobody knew about this. Well, actually, maybe some people did know about it, like certain government agencies, but they weren't letting on. But nobody knew that this was doable until this was published. And suddenly loads and loads of chips and microprocessors were vulnerable to this kind of stuff. So, horrible. Some more bad news, testing. You'll hear me rattle on about testing quite a lot. We all like testing, right? It's a good thing. But there are some limits. The basic rule is that Satan's computer defies testing. It will always beat you. No matter how hard you try, the basic assumption you need to make is that bad people will find a system state and some input data that you haven't tested. And given that any non-trivial system has trillions of states and trillions of sequences of input data, don't tell me you're going to do lots of testing, because I don't believe you, basically. So stuff like Heartbleed, for example, millions of people a day, billions of people a day were using OpenSSL, seemed to work all right. That's lots of testing. Yet for 2.5 years, an appalling bug was in that code. No one noticed. This also negates the so-called many eyes theory, the open source idea that if you've got enough people looking at the code, you'll find all the bugs. Nah, it's nonsense. Doesn't work. Heartbleed defied 2.5 years of people looking at the code. No one spotted it. Oh, that's a bit of a blow as well. So if I talk about security to anyone about software, and people say, yeah, our software's secure because we've tested it lots, big alarm bell goes off in my head, okay? And I just think, nah, sorry, not good enough. I say, what else have you done? And they say, no, we've tested it lots, okay? It kind of doesn't stack up logically, because Satan's computer's going to get you, basically. This is a problem. Limits of talent. Who's a good programmer? Come on, own up. Who thinks they're good? As developers, we all need a really healthy dose of modesty and realism in what we do, okay? We all like to think that we're good, okay? Unfortunately, you're not. Nobody is that good, okay? A couple of years ago, I looked at the third row from the back, a poor chap called Seth. Hello, Seth. I led a software development team, and Seth was my first team member. And I trained Seth in some of this stuff. And there's this training program called Personal Software Process, which is really good. And I put Seth through this training program, which basically is a training program in discovering that you're not nearly as good as you think you are at software engineering. And it's a kind of humbling experience because you realise how many mistakes you make. And you think, oh, hell. I hope Seth survived. He's here. He's turned up today. So you're not as good as you think you are. There's also this problem about another testing issue, is that testing provides what we call confirmation bias. And I can illustrate that with a famous programmer that we all like, this gentleman. So Beaker here thinks, well, yeah, I'm a really good programmer. I'm really cool. I'm really good. He then thinks this, because, gosh, he's super sexy and cool. He's up to date because he's a test-driven developer or a test-first style developer, and we're all told that's a good thing. So he's done his testing and written some test cases and added them to the repository, and they all pass, marvellous. And so he thinks, marvellous, aren't I clever? And he goes to the pub, he goes home, thinking he's finished his job. This is not a great situation to be in. This confirmation bias problem is, testing's great, testing, you run some test cases and you think, woo, it all works, aren't I marvellous? And off you go. It's not really good enough, especially, as I said, on Satan's computer, it's never going to be good enough. So here's another technical problem, something that's close to my mind at the moment, is I'm looking to buy one of these. My wife said, should we go and get one of these things? This is a video baby monitor. So I said, do you want the one that's going to be turned into a botnet and attack the DNS servers? Or do you want the one that's not the botnet one? So I went online and I can discover, it's quite expensive one. There's the Motorola one and the Samsung one. They look about the same. This one is £6.50 more. So is this one £6.50 more secure than this one? So I did some digging on Motorola's website and I found this. And it says, yes, it's okay because, yes, it's digitally secure. And I think, oh, marvellous. That fills me with confidence that they've made some grand claim that it's definitely secure because it's got extra digital stuff in or something. And clearly this is fatuous nonsense. In the automotive trade and in economics, this is called the market for lemons. Okay, in the used car trade, it's called the market for lemons. So a lemon is a crappy used car. The problem is, as a buyer of used cars, you don't know it's a lemon, and you can't tell it's a lemon because it just looks like a car, right? You can't tell if it's, got, whatever, something wrong with it inside. The seller might know that it's a lemon, but they're not telling you. They know more, but they're not letting on. So that's the economic thing is called the market for lemons. So this gentleman, for older people in the room, obviously, older people in the room, so sort of, would you buy software from this gentleman? Say, oh yeah, it's really good. We've tested it, lots, honest. Well, yeah, and it's the market for lemons is this picture. I typed market for lemons into Google Images, and that's what popped up. So good. Obviously a blatant copyright violation, but never mind. So what can you do about it? Well, there are some things that don't work. We know from bitter experience. This comes from years of trying to build safety-related systems. Some things we know don't work too well. Saying, oh, well, we'll test it more, or we'll be more careful, honest. that kind of doesn't add up, especially not at the scale we're talking about. We've gone, in safety critical systems, we've gone from a few thousand lines of code now to, in a car, goodness knows what, 100 million lines of code in a modern car. How could you possibly say that you've adequately tested this kind of stuff? So testing it more doesn't really work. The real problem is, how do you know when to stop such activity? You usually stop testing when you need to ship the product or when you run out of money, or when you go out of business, possibly. And that's not a great termination criteria. Some of our clients say, OK, we don't need all this technology because we only hire really brilliant people. You'd be amazed how many of our clients only have above average people. It's astonishing. It's actually statistically amazing. So, OK, especially for startups, sometimes it is possible to say it's OK because we've only got a team of 3 people and they're all brilliant. That is actually possible. And even with totally substandard technology and languages, brilliant people can do fantastic work. That's illustrated by the Linux kernel and LaTeX and some of the stuff that has been around a long time seems pretty reliable, right? And is written by brilliant people. So if you can hire Linus Torvalds and people like Sophie Wilson, do, because they're brilliant. So hire them. That does not scale. You can't rely on that as your organisation grows. You can't say it's OK, we'll only hire the top 10 most brilliant people in the world, because you can't get past 10. So this doesn't really work. And as software grows in complexity and scale, it stops working anyway, because some people, no matter how brilliant, just can't see all the bugs and be relied on. OK, so finally, get to some good news. Some good news. Oh, here's a line to chill the heart and possibly empty the room as well. The idea that maths is your friend. This is a radical idea in software engineering, but not very radical. How many of you studied electronics at university? I did some electronics first year. I was a computer science person, right? But I was forced to do some electronics. First year electronics, and I did it anyway, was a thinly veiled mathematics degree. Because if you couldn't live and breathe differential equations and complex numbers and fast Fourier transform, oh my God, it was brutal, first year electronics. It's all maths. So why is this idea so weird in software development to say, oh, we're going to use maths? So it shouldn't be a shock. So we do something for safety-related systems and security-critical stuff that we do. We use this idea of analytical verification. So sometimes this is called static analysis or static verification. So the idea is you use tools on computers to not test and observe the behavior of programs. You analyze the programs as a mathematical entity using the semantics of programming languages or the semantics of design notations. Like, how many of you use MATLAB Simulink, for example? So you can analyze MATLAB Simulink stuff and decide what it does and decide if it's good or not. But we can analyze programming languages too. If you get it right and you use the right languages, these tools can sometimes find all the bugs. So that's called soundness of verification. So would you buy a tool that said, I've tried my best and I found some of the bugs? Well, OK, maybe. That's a good thing. Better than nothing. Or would you buy a tool that said, there are definitely no bugs in your software, so no buffer overflows, or no division by zero, or whatever? So clearly the latter sounds like a better proposition. The latter case is actually much harder to achieve technically. It requires a level of discipline and commitment that most people find unpalatable, frankly, because it actually requires some real guts to do it. And also it has this nice side effect that if you get rid of all the bugs, and this is being done by the developers on their desktops, this is a pre-commit activity. This is not done by your integration server or some other team. This is done by developers. The moment they write code, you check it through some clever tool. The tool says there's a bug, so you fix it, and it's done. This is much cheaper because you get rid of all the bugs as a development activity, and it's just a lot cheaper at that end of the life cycle to get rid of this stuff. So it's a real prevention style of development. This really, really does work, and this is how we choose to develop safety-critical software. We've done all sorts of stuff, and it really does add up. So this kind of approach is used in systems like the Typhoon aircraft, which you'll see bombing around the sky sometimes and causing sonic booms over Birmingham and that kind of stuff. The Typhoon has this kind of software verification going on. Yeah, don't be afraid of the F word, folks, the formal word. It really is your friend honest. Don't be afraid of the maths. The tooling has come along in leaps and bounds in the last 10 or 15 years. It's astounding now, just given 10 iterations of Moore's law, what we can do with a theorem-proving tool or an analysis tool. It's astonishing. Here's an example. This is the air traffic control thingy that we built. X-axis shows time relative to now, so that's no minutes from now, meaning now. That's 2 minutes in the future, 4 minutes in the future. The y-axis shows nautical miles of separation between things like aeroplanes. So, for example, this icon here shows an interaction between Virgin 44 and British Midland, whatever. So in 11 minutes' time, those two planes will have a separation of about 4 nautical miles, and the two arrows pointing in the same direction means they're catching up with one another. That's bad, but it's 11 minutes in the future. So an air traffic controller will go, okay, they will call up Virgin 44, tell it to do something like climb or turn, or whatever, and this will disappear because the conflict will be removed. So this is giving air traffic controllers about 15 minutes vision in the future of what's going on in their sector of airspace. It's basically predicting where all the aircraft are going to be in real time into the future, and then doing collision detection on all of them, and then mapping this all out onto this picture for the air traffic controllers. It's an astonishing thing. We built this. This is the thing we built that doesn't ever crash. There's 250,000 lines of code behind there. I know it doesn't look like 250,000 lines of code to draw one little picture, but it's an easy example. There's 250,000 lines of code driving this system, and it's a pretty amazing piece of engineering that the guys in Bath built. So that's one example of the kind of stuff we do with this analytical approach. Yeah, you're probably thinking, yeah, come on, hang on. This can't be real. There must be some horrible catch from the hecklers, Statler and Waldorf. Well, okay, there is a catch. Some golden rules. Garbage in, garbage out. If you try to analyse crappy software, you get crappy results. And you also get a lot of false alarms. You'll get a lot of results that say, warning, software might have a bug on line 10. And you go, that's no good. The problem really is to develop software that's great, beautiful, verifiable, correct in the first place, so that as you analyse it and when you analyse it, you've got no bugs. So there's no magic bullet. There's no tool that will magically fix your software and make it better. You still have to think, I'm afraid. No verification without specification. There are some common implicit specifications in most programming languages. Most programming languages say stuff like, well, don't have buffer overflows, don't divide by 0, don't have arithmetic overflow. Those are implicit and should be true of every program you ever write. Beyond that, you have to think what you want. If you want to verify some property, well, you've got to write that down. That means, God forbid, doing some requirements engineering. Shock horror. More than just a story, more than just a card. You've actually got to think really hard about what is that security property? What is a valid query to your database? Well, yeah, work it out, write it down, and the tool will be able to check it. But you can't skip the thinking, basically. That's the catch. Adoption of this approach requires some discipline and a sort of change of lifestyle for a lot of developers. So crazy ideas like learning a programming language that you've never heard of, because it's not that fashionable and cool, but God, it enough work. And some of you, may have adopted test-driven design. That's a cool idea. Good things, a good discipline. But why not generalise that to a verification-driven design, to adopt all the types of verification that we might want to use, including static, dynamic, coverage, traceability, robustness, performance, penetration, all of those styles of verification. Design to make your software work for all of those things, not just test. There's a lot more to the world than test. Why is it hard? So why this is the techie bit. There is a bit of technical stuff coming. I'm going to put one line of code on the screen in this talk. One line of code. Why is this so hard to do with, in quotes, popular programming languages? Most programming languages were not designed to have this analytical verification applied to them. In fact, they seem almost maliciously designed to defy. They're sort of Satan's programming language as well. Why is it hard? Basically, the big problem is this issue of ambiguity. It's a nice idea that you know what your program means. Seems reasonable, right? Unfortunately, most programming languages, you don't know what it means, because they're full of things that you don't know what it is. You might think you know what it means, but you don't. So to give some concrete example, how many of you, this would be interesting actually, see what this straw poll is. How many of you are familiar with C or C++? Okay, that's a pretty good number. I thought that might have come down a bit in the last few years, but maybe not. Oh well. I would treat it as a good thing if no one puts their hands up. When everyone says, no, we're using whatever, something else. We're using, if everybody's moved to Rust or NIM that we'll hear about later, or Go, that will be a good thing. Okay, but, oh, never mind. So, C or C++, quiz time, dudes. So in C or C++, if I have some declarations, I have a variable called I, which is an int. I have a variable called A, which is an array of 10 ints. So just in your head, don't shout out the answer. And then I've got some code. What does that mean? What does that mean? And you can't compile it and see. That's cheating. Just statically, in your head, what does that line of code actually mean? So who thinks they know what it means? Stick your hands up. Come on, be brave. Who thinks they're really sure, 100% they know what it means? Okay, who's not sure? Okay, so I'm just going to randomly pick on you, sir. Oh, why aren't you sure?
Because I'm not too sure. I doesn't seem to have been, for a while now, initiated to anything.
Okay, so let's assume up here I has been initialized. Let's assume they're both initialized. Okay. But still, what's going on here that makes you a bit concerned or worried or anything? Yeah, okay, that's enough. Ambiguous. I don't know, yeah. So this is a problem. What's going on here is you've got two side effects to I. There's I++ is a side effect to I, and there's an assignment to I. So what you've got is two side effects, and what's here, invisible there, is a thing called a sequence point. And how many of you are now thinking, oh, what's a sequence point? I've never heard of a sequence point in C. God. This code, according to the definition of C, this code is undefined behavior. Okay? There is no semantics of this code. You cannot decide what it means statically. Even compiling it is not a reliable test of determining what it means because your compiler is under no obligation to be consistent at all. These are also context sensitive. So if I change a line of code up here, the meaning of this line might change. And undefinedness is a black hole in your program. Once your program becomes undefined, that's it. All bets are off. You cannot recover. So the classic undefined behavior is buffer overflow. And that's, the thing that's commonly exploited. Once you've got a buffer overflow, you're dead, semantically. The problem for us people building tools, I'm trying to build a static analysis tool that determines if this program's got bugs in it or not. I hit a line of code like that, and I'm stuck. All I can do is refuse to analyze the program, which is truthful, but puts me out of business because no customer will buy my tool because the customer says, oh, your tool's crap, it can't analyze my code. My code's right. This is code that seems to pass testing, of course. Or you guess what it means, which means half the time you guess wrong because your compiler does something else. And then you just get the wrong answer. So you just mislead the customer down some sort of unsoundness. So this is disastrous, basically. That's why it's hard. Some more good news, though. Better can actually be cheaper. There is an assumption that high-integrity software must be really expensive. This is not true. If you get it right and avoid the waste in software engineering is putting the bugs in, finding them, fixing them, and then doing all your testing again and again and again. Using testing as a debugging mechanism is insanely expensive. If you get rid of that by going to a sort of preventative zero tolerance approach, you get a better product for the same money, or possibly even less. It's astounding. Producing better quality software is actually cheaper, which sounds counterintuitive, but does actually work. How do you avoid a lemon? If you're buying a used car, how do you not buy a lemon? What do? Use the AA. You get an expert to inspect the product. Someone who knows what they're doing. He'll take the lid off, open it up, and somebody that can look inside. So you use analysis. Good. What else might you do if you don't want to buy a lemon? Yeah. That's more analysis, I should imagine. Yeah, you analyse the log of the product. You look at it. I mean, cars used to come with a big book, the maintenance log. Car used to come with paper. These days, you plug the laptop in and see what diagnostic data you get. You do that. What else might you do? Yeah. Test drive. Take it for a test drive. One more thing you might do. That, very commonly, reputable garages these days will give you a warranty with a used car. And they say for a year that car will be all right, and if it's not all right, we will fix it for free. So what that does is it moves the risk from the buyer to the seller. The seller therefore has a responsibility to kind of honour the warranty, and that's putting them at risk. For software developers, your challenge is to bloody well do it and deliver your software with a warranty. I know that sounds like a nuts thing to say. At Altran, we have done that. We have given our customers a warranty with software. We said, if there are any bugs in it against this specification, we will fix them for free. And we've honoured warranties like that with software. It is not out of the question to do that in software. You need quite a lot of confidence, but it's doable. So set requirements formally, something that you can know with a yes-no answer. Is it a lemon? Yes or no? And with some actually well-defined concept of what is or isn't a lemon. You assess the product. So yeah, get somebody competent to take the lid off and have a look inside. In other words, that. I assume you know who that is. That's Linus Torvalds. And he famously once said to one of the developers, he said, talk is cheap, show me the code. Meaning, don't show me your PowerPoint about your process and your metrics. Show me the software and you'll know if it's good or not. That works to some extent. For me, show me the software, I will show it to my theorem proving tool. And my theorem proving tool will have a good look and see if it's good or not. So show me the code. Get the source code. It'd be amazing how many government departments in the UK buy software but don't buy the source code. Unbelievable. We bought 8 helicopters once and didn't get the source code. So they sat on the ground for 5 years. They were unflyable. Because Boscombe Down, the AA of military aircraft, could not assess that the software was fit for purpose. So they said, no, those aircraft can't fly. So we had 8 Chinook Mark IIIs parked on the ground at Boscombe Down for about 5 years. That was about 300 million quid down the toilet of taxpayers' money. Bit worrying, that one. Yeah, put this stuff in the contract, and if it doesn't work, put penalty clauses in the contract. Why not? So a future. There's no silver bullet, but quite a lot of this stuff we really do know how to do. This analytical verification model, this thing called personal software process, this kind of zero tolerance approach to defects management, really does work. We've been doing it for 20 years in safety critical systems. So you really ought to give it a crack if you're building anything that's security related, because security critical stuff's worse. Remember, Satan's computer is much harder than Murphy's computer. Will the market, decide to adopt this style of engineering? Well, for the last 20 years, the simple answer is, yeah, it doesn't seem to work yet. We're waiting for the market to decide. The insurance companies might decide on your behalf. The courts might decide on your behalf. If we have enough Toyota moments in safety-related computing now, we often talk about, when is the whatever industry going to have a Toyota moment? And the Toyota moment is when a court fines a big company for a huge amount of money. That might cause something to change. Thank you. A final thought. This chap said that, and you might think, huh? Guy from Altran's gone mad again. What's he saying? Here's a formal language that you all use. It's in every single one of your pockets right now. Anyone recognise that language? Which assembly language? Wrong. What? ARM. ARM assembly language is formal and it's in your pocket right now in your phone. Every single one of you uses that formal language. All our software ends up running on a formal machine. So you all use formal methods. So the big question is not if, but when to start using formal methods on your project, which is kind of an interesting way of looking at it. Homework-wise, I'm going to show you a picture of a surgeon. Hey? Surgeons get stuff right most of the time. If they don't get stuff right, they suffer extraordinary penalties. They go to jail or they lose their jobs. So how do they do it? How do they manage to do something incredibly complicated and mostly get it right? If you want to know, read a fascinating book. This is Atul Gawande, who is a professor of surgery in Boston. This book, called The Checklist Manifesto, I will draw the subtitle to your attention, How to Get Things Right. Read this book, translate his advice into software engineering. It's a wonderful book. It's not about software, but it's about medicine, but it'll persuade you not to go into hospital. But it's really, I shouldn't say that. It's a fantastic book really about engineering. So take a look at that. Right. Question 1, is this my cat? The answer is no, but I like this picture because it blinks at you and taps its paw. That's my cat. But we'll go back to the tapping cat. Are there any questions? I will let the chair decide.
Let's start with the gentleman with the white lanyard. Yep,
The white lanyard, that's everybody. What are you talking about?
Brilliant, isn't it? I could formally pick a person.
I don't know.
Yeah.
Go ahead. Who's got the mic?
You
have, sir.
There you go.
It's me then. You mentioned Rust, Nim, and Go for languages that we could look at. Is there one that you'd put top of the list for a good language to look at?
Well, I'd put my own one. The one that we use for doing the really critical stuff is a language called, I have to be very careful, it's a language called Spark, but it is not Apache Spark. That is nothing to do with us. Apache just used the name more recently, and we had it long ago. It's a language called Spark, spelt with a K on the end, but it's not Apache Spark. It's desperately unfashionable. It's related to a language called Ada, which is related to a language called Pascal. The older people in the room, Pascal. But Spark is awesome. That's all I want to say. But it's like Rust, but much better for embedded systems.
Okay,
and that's the language with the really cool theorem proving and static analysis stuff. And it's open source, so you can play with it. But Rust is good. Go's really interesting. Rust is doing some very interesting things. And I'm really looking forward to hearing about Nim in the next session, because that's going to be interesting too.
Yeah, anyone who's interested in Nim, it's the next talk in this room. So, otherwise, thanks very much for being here, and join me in showing our appreciation for Rod.